I'm going to take that last beep. It's like listening for popcorn in your microwave. You don't want to wait for too long between the pops or it all burns. As my cue to kick things off. So welcome everybody. Thank you so much for joining Modzy's second inaugural, however first official Tech Talk. If you're just joining us for the first time this week, one of the things we're planning to do with our Discord channel is start introducing opportunities to, on a regular weekly basis, just talk about different tech topics related to the world of artificial intelligence, machine learning, MLOps, with the hope that it provides an opportunity for us to share some of the things we've learned at Modzy. Some of them are related to our product, some are just related to good ideas and hopefully painful lessons we've learned that might be useful to others out there. Also an opportunity for us to share some cool things that our partners or some of our customers are doing, and also as an opportunity to just converse and talk to other folks in this field, and really learn more what other machine learning engineers and practitioners, data scientists, app developers are working on. So these tech talks are, the intention is that they'll evolve. And one of the things I'd love to ask is if you have an idea for something you'd love to talk about, maybe a topic in the AI ML space that you don't feel like gets enough coverage, we actually have a channel for Tech Talk ideas, and would love to get your feedback and suggestions on what specific topics might be of interest. So please share your ideas there, and let us know what you think. So a couple things. Welcome. We're, again, really pleased to have you all here. Every Friday at 1 p.m., we're going to be meeting for the first year. That is our commitment to trying out this experiment. And we'll maybe try some different formats, but for now, probably just kind of some talks, some slides, and then after each one of these talks, we'll have an opportunity just to hang out together on the general channel. So after the talk's over today, which we'll be talking about kind of an intro to ModelOps, if you'd like to head on over to our general voice channel, feel free to do so. We'll be meeting there to just kind of discuss the topic, ask each other questions, share ideas. So, hopefully a good opportunity just to kind of connect as a community. I think that's everything I had for the intro. So this is our week 2 and first official. So let's go ahead and get started. Before we kick things off, the final thing I wanted to mention is we have some upcoming talks already planned, already in the works. So next week, we'll be talking about how AI can more easily get integrated into applications. So some live coding examples, some kind of live app demonstrations, which should be fun. And at the end of the month, we're going to be covering explainability, which is a topic that gets more and more interest in a whole bunch of different industries we've spoken to, which is basically the idea of how do you figure out how to understand how a machine learning model, an AI algorithm, is making its decisions. So that should be really fun. And then early February, we've got a talk planned. We're still picking what topic we're going to do. If you have any votes you'd like to share, again, send those over to our Tech Talk Ideas channel. But we might be looking into exotic hardware. We might be talking about some tips and tricks for writing APIs in Go. We'll see what happens, but stay tuned. All right, so today we wanted to talk about ModelOps and really just provide an overview. If you are a seasoned MLOps practitioner, I probably will not share anything that's news to you. What I hope that we're able to share with you, if you're really on the seasoned end, is some of the things we learned, some of the lessons we've picked up along the way, and maybe some either new tools or new approaches that you might not have tried before. If you're brand new to the field, if you're brand new to this concept of MLOps and you don't even know what that means, awesome. That's exactly who this talk is targeted for. So we're really excited to give you an opportunity just to kind of get your feet wet in this field and learn more about what people mean when they're using this term ModelOps. So there's a number of terms in this whole kind of alphabet soup of AI jargon that you might hear kind of interspersed instead of ModelOps. There's AIOps, there's MLOps, there's DevOps for AI, there's DevOps for ML. I think a lot of those terms are still getting worked out, and the differentiation and the definitions between them are honestly not yet codified to a degree where I think it matters spending a ton of time trying to define the nuances between each of them. So, us here at Modzy, we've kind of just leaned on the term ModelOps as our general catch-all for the process of building, running, and monitoring AI models of any kind, and then the transitions between each of those steps. So, basically, you got a whole bunch of different folks working on different parts of this problem of using artificial intelligence in a larger system, a larger ecosystem, to solve an important problem. Typically, a business problem if you're a business. If you're in sort of the public sector or government, it might be some sort of challenge related to your constituents and your citizens. So what ModelOps is really oriented around is applying what the tech industry has learned about DevOps over the past 10, 15 years or so to the world of machine learning. And because of some things we'll talk about, some things that make machine learning unique and interesting, it's not always a one-for-one swap. We can't always take everything that's done exactly how it's done for traditional software and apply that same approach to machine learning models. And so as a result, you end up with this divide where you get a bunch of really smart and talented data scientists kind of working with tools over here on this side of the chasm we're looking at. This involves taking historical data, analyzing this data, labeling and training labeling this data, and then using it to try to train and create algorithms that can be used to either predict or classify or generate an output based on new data it's never seen before. There's a whole bunch of techniques to do this. Probably the most compute intensive and maybe sophisticated versions of this include deep neural networks. But really this can include any type of model that you create, even a linear regression that takes in a bunch of X values and pumps out some Y values. All of that is kind of here on this left side. On the right side, we have sort of all the tools and technologies that an application developer that's building scaled applications, whether they're in-house, like inside your company, or customer-facing, these are the tools that application developers, cloud architects, cloud engineers are working with. But because of these two worlds kind of developing on their own in different ways and coming from different locations, it's left a gulf. And that gulf is really what ModelOps is trying to solve. It's really trying to connect these two worlds and connect all these different people together in a way that makes this more possible. So some folks will refer to this gulf as the AI Valley of Death. And in the world of artificial intelligence, the Valley of Death kind of refers to this idea that there are a lot of smart, hardworking, and talented data scientists building amazing models that do all kinds of cool stuff. Churn prediction, if you're looking to find ways to hold on to and retain your customers. Vehicle detection, identification, and tracking to support autonomous car navigation within a crowded city street. Satellite imagery analysis to help identify wildfire coverage, acreage, as well as regions that are at risk for catching wildfires. All really cool and interesting and useful algorithms. But the challenge is how many of those ideas, how many of those models have actually made it into a production system where the data you need to process through those models is actually connected and the whole thing is kind of running smoothly, can be updated on a regular basis, doesn't require a ton of manual work to get working. And the answer is it ends up being not that many. So what are some of the things that hold back or contribute to this gulf between cool machine learning models and reliable production software? We sort of break it down into three big buckets. One is teamwork, two is empathy, and then three is process. We'll spend the majority of our talk kind of going into process things, but I think it's really important to note that your process is only going to work if it's supported by a sort of a team-based mentality and the empathy to better understand and kind of figure out and learn what all the other peers in your organization that have a role to play in building AI-powered apps, what their work is like, and how we create a process that allows all these different players to work together and also understand where we're trying to go and what kinds of challenges we're trying to solve. So process-wise, this is what a ModelOps process might look like at the highest level. And so this kind of goes from the data side of the world, data preparation and organization and cleansing and labeling, through the training of a model, the versioning and management of model artifacts, the building and deployment of these models as their own microservices, and then the running and monitoring of these models in the real world against real production data. And these patterns follow a lot of DevOps patterns, as many of you who have been in the software world and DevOps world for a while have seen. But they have some nuances that are specific to the machine learning ecosystem. So kind of up front, we have what you might think of as the data science phase. And I would also include the data engineering phase. So an important part of ModelOps is making sure that you've got some of the tools in place in order to help automate and reduce the friction required to take your historical data, whatever it might be. It might be huge volumes of imagery if you're working on computer vision models. More frequently, more often, in fact, it's giant historical structured records. It could be records from a customer database on every single customer and every single purchase that they've made. That information, while is essential for training a great model, it's often in a very difficult to access format or location, or has a lot of rules and regulations around who can use it and when and what you can touch. So if you're going to build a ModelOps pipeline, it's highly worth the effort to hire some good machine learning engineers and data engineers to work on providing really simple mechanisms for that data to be accessible to data scientists so that they can work with that data. A lot of data science comes down to just figuring out what the data has in it and what features exist, and doing a bunch of statistical analyses to see how the data set is distributed, to really understand what kinds of features are worth using if we're going to create a model to predict something like customer churn. Alternatively, it's important to understand, if you've got a computer vision data set, what's the distribution of classes? Basically, how many cats, dogs, and monkeys do we have in this data set? And if we only have 2 monkeys but 1,000 cats and dogs, it's probably going to do a pretty poor job at classifying monkeys. So making sure that you've got a good process and flow between your source data, which is often in kind of ugly but stable databases, into the tooling that data scientists can use. That's the first, I would say, step towards success. So really important work to get those data engineers and the data scientists on the same page. From there, I sort of skipped over this part because I think in the machine learning world, this is assumed, but magic happens, and that magic is data scientists take that data and then develop algorithms. And they're probably going to develop a bunch of algorithms, probably develop numerous models using different data, using different features, using different characteristics of this historical data to create a bunch of different models that they'll test against a holdout data set, basically a piece of that historical data that was not used to create this model. And by doing so, you can kind of build 10 models, test them against each other, and then find the top 2 or 3 performers based on whatever factors are most important to you. Sometimes it's accuracy. In other cases, it might be speed. And those 2 things are actually very important to balance because sometimes very accurate models that are slow ultimately don't actually matter. So data scientists will do all that work, and finally they'll have 1 to maybe 5 versions of a model where they're kind of ready to go and test them out in the real world. So this is where the field of machine learning engineering has really exploded. And this is the process of figuring out, how do you take these assets? What does a model look like? It's typically some in the Python ecosystem, some Python files, maybe a weights file, and then references to other Python code, other dependencies and libraries needed for all of that code to run. But if you want to use that code in production, you either have to manually turn it into a service each and every time, which typically it's not something that data scientists have a ton of experience with. They're great at working with data and training models, but if you ask a data scientist to take all of that code and turn it into a scalable service, well, now you've asked them to learn a whole new set of skills, and that typically includes learning about Docker and containerization, understanding how web services work, understanding how microservice architecture works. In sort of modern ecosystems that rely on tools like Kubernetes for the orchestration and scale of all these containers, now they have to learn Kubernetes, which is a giant hurdle, Even experts in Kubernetes would prefer not to have to deploy their own version of Kubernetes. And so you're starting to put on this whole other set of responsibilities and skills a data scientist has to pick up. They're typically not super familiar with. So machine learning engineers come in and often provide the glue to help tie this stuff together. So that will often look something like this. You might have a mechanism where the resulting outputs of a trained model, these Python files, weights files, references to libraries, other pieces of data, are versioned together through some sort of versioning system, and then processed through an automated build process. So this becomes really helpful if you're in an ecosystem where you expect your models to need to be updated on a regular basis. So for instance, if you are doing, I use this example because it's so common, customer churn prediction, you often will be doing these scoring exercises on a regular basis, if not each week, certainly each month, and maybe even each day, in order to determine, have a customer's behaviors changed, and do different types of behaviors now help us better predict churn, or basically when a customer stops using our service. So those models need to get updated regularly. If you're doing that by hand, and you have a great team of machine learning engineers, they can help turn those models into services. But if you're doing it by hand, it's going to take a long time, and doing iterative updates, it's just not going to happen quickly. So building in an automated build process is a key part of making sure that you can respond quickly, and that as old versions of models start to kind of lose their magic, you've got a mechanism in place to very quickly update and then deploy new versions. And finally, once you've kind of built these containers, you can then distribute them to really wherever you'd like to host all these images. So these are some of the key pieces involved in making that gulf kind of connect from the data scientists all the way to your app developers. The other thing I'll mention here, there's a lot of other crazy stuff going on behind the scenes that machine learning engineers spend their time working on. And this includes understanding the hardware that's available. Where does this model actually have to run? What chipset are we working with? Because you have to actually compile the code differently for an x86 chipset, basically what Intel uses, versus an ARM chipset, which is used by a lot of kind of commoditized hardware. Alternatively, do you have GPUs available? Was this model trained to run specifically on Google's TPU? Was this built for some other crazy exotic piece of hardware? Machine learning engineers are often the experts in that, and they spend a lot of time making sure that that code is guaranteed to run in the final location where it's going to be hosted. And they spend a lot of time typically doing performance analysis. So your machine learning engineers are often kind of your pit bosses, if you're in an F1 team, to analyze all this data and make sure that the performance you're getting out of this model is kind of like maximized. Finally, this takes us kind of to the last piece, which is the integration phase. And this is at the point at which you've got your model, it's kind of ready to go. Now you actually need to deploy it so you can start running data through this model. If you're not sort of used to this or familiar with this ML engineering and AI world, we use the term inference, which basically is the idea that a model is inferring, based on a new piece of information, some prediction, some output. So in the case of a linear regression, it will be taking in some numbers, and then it will be producing some other output number. So that could be your height based on your age. Is a linear model, and it will be making an inference. If you tell the model how tall is an average 2-year-old, it will put out an inference. In the case of a computer vision model, that inference might be the classification of an image. This is a picture of Paris. In a audio world, that inference might be the translation of audio into text. All of those count as inferences. So this kind of part of the process is where you really start to bring your machine learning model to the system that has the live production data that needs to use these models to do a job, to solve a problem. And then the last piece, which is really an important part of it and can get overlooked if you don't plan out ahead of time, is the production monitoring. Models have lifespans. They need to be retrained. They need to be improved over time, typically. And you really want to have that monitoring in place well in advance, so that as you put these models up there and they're doing their job and they're taking in data and spitting out inferences or predictions, outputs, you can keep track of that. And when things start to go south, you have tools to let you know, hey, this model is not as healthy as it once was. So within this stage, we talked about this a little bit. Model deployment is the idea of taking kind of this packaged output that your machine learning engineers have so kindly put together, this kind of container or other commoditized unit of code and software and dependencies that's ready to run. And you really want to put that in a place where it can be deployed in a scalable way, so that as demand increases for this service, typically you'll treat each of these models as their own services. You can scale, and doing so with a standalone web server, for instance, ends up being a bad solution. If you think your company is only going to ever use one machine learning model ever, maybe you can get away with that. It might be fine, but odds are pretty good that if you're successful with AI and machine learning, more projects will follow. So having a tool that lets you deploy and manage multiple models on a range of hardware ends up saving a lot of time in the future. So production inference, again, this is the idea of taking that model, giving it new data, and predicting a result. This is important. One of the other important pieces here is to think about security, because machine learning models can be stolen through something called model theft. So when you have these models up for inference and you're building out your pipelines, try to remember that if the APIs you make to allow you to access these models and send it data and get results, if they're not secured, a bad actor can actually go in and essentially mine your model for its decision-making prowess. And that's a real risk, especially if that's proprietary information. In some pretty sophisticated attacks, sometimes attackers can even figure out what data you trained this on, which would actually be a vulnerability leaking your customer information. So production inference, important to get it right, and important to make sure that you're securing it correctly. And then finally, production monitoring and retraining. So some of the things that you might want to think about monitoring will be things like just the performance of the service itself. You have this model, you send it data, you get a response. How long is that taking? How many inputs can this model, this service, handle at once? Is it one at a time, or can you saturate a GPU and have it process 15 inputs simultaneously because of the way GPUs work? What's the total inference time? How much latency is there? How much time are the inputs waiting in queue? How much time does it take for the inputs to get downloaded to the service? Does that service need to be relocated to be right next to the data? Hugely important questions, really related to just kind of speed, peppiness of your services. But data scientists are also going to want to look at some other metrics, and this includes things like drift detection. So drift relates to the idea that as models are in production for a long time, the world changes. The world is constantly changing. So the models themselves, nothing's changed with the model, but the input data it's used to seeing looks different. So you're going to want to be able to monitor for drift and get information and alerts when your models are losing their performance. And this also can include some other specialized things like explainability, which gives you an opportunity to get both a quantitative as well as ideally a human interpretable answer as to why a model has made a certain prediction. And in some industries, it's actually required by law. In certain kind of sectors of banking, if you tell someone that they're not qualified for a loan, you actually have to provide an explanation, a reason for why. So if you're doing all of that algorithmically, explainability becomes a really useful and important tool. And all of that data, performance in terms of kind of just speed and peppiness, to the drift found within the model, to the outputs explanations, all of that can help you identify when a model needs to be retrained. And then that really creates this life cycle. So from there, you have a model, it's been out there, it's been doing its job really well, but it needs a tune-up. Once you have that information, you can actually kind of take your model back to the beginning and retrain it with new information. And ideally, you've put in place a system and a process where you can then use the new production data that you've been collecting, right? This model's been out there, it's been live, it's been taking in data and generating inferences. You should try to use that data as much as you can to then retrain this model. That might require some labeling, but that really becomes the best way to help make sure that your model's constantly getting better and is getting better specific to the kind of data it's used to seeing. Now, there's a whole bunch of different tools that you can use to put all those pieces together. I have really, this is a sampling just to give you a sense of what kinds of tools might be available to help put these pieces together. I don't think there's a one-size-fits-all solution. Maybe someday there will be. Maybe this will be more commoditized. But because of how quickly machine learning is innovation kind of is rolling out, how fast we're discovering new types of models, new types of approaches, how quickly even new hardware offerings are made available, makes it very difficult to kind of norm and standardize on like the tool or the tools to do this. And even making decisions between when to go open source and when to go commercial. These are hard questions to ask. So for each of these, you can just see some examples of the kinds of tools you might want to consider when it comes to building this MLOps, ModelOps pipeline. And in some cases, the commercial tool is really going to be the best bet. Typically, commercial tools are really helpful when you want to be able to have something as a managed service. You want to have another expert help you make sure things work out really well. When sort of security governance and accreditations are really important. Or when you don't want to absorb the cost, risk, and sort of long-term maintenance of building your own tool or managing your own kind of custom deployment of open source. On the other side, open source software, pretty awesome. There's a lot of great open source software out there. Much of it can be managed very affordably and very efficiently. So kind of for each of these boxes, it ends up being a decision that you have to make based on your use case and your organization's sort of risk tolerance as to when you choose commercial versus open source. So just as an example, this is actually how within Modzy we do our sort of internal ModelOps pipeline. So we use a combination of tools, and this is just a representation of a couple of them, but this is kind of our standard pattern. So we host everything on AWS. Our data scientists use a combination of Jupyter notebooks. They'll choose a library of choice. In this case, we're looking at sklearn, and then they'll use Jupyter to manage their experience and sklearn to train models on historical data, and then manage all of that within GitHub as our source code. From there, we use an open source project called Chassis to then take those outputs and convert them automatically into a container. And so this is something that can be really helpful so that your data scientists or even your machine learning engineers don't have to spend a ton of time manually doing that exercise, manually taking all those model artifacts and turning them into a container. From there, you can send it to your model registry of choice. And then finally, we use Modzy, of course, to actually deploy, run inferences, and then monitor those models in production. And from there, you can then start calling those models via API. So that can be from other web and mobile applications, from commercial software, from back-end processing pipelines, CLI tools, you name it. Really, however you want to call those models, you can do so using something like Modzy, which provides an API endpoint. And then to kind of bring it full circle, once your model is out there for a while, you start to see drift, you can then send that production data back in to the cycle of retraining that model, maybe taking version 1 and forking it to create a version 1.1 by relabeling that production data, storing that data in something like S3, in probably a computer vision example. In the example of a more structured data set, you might use something like Hopsworks to actually engineer your features, which is kind of a translation process that makes the model training more repeatable and easier to manage. And then from there, you've got another model you can send back through this process. And all of this can be orchestrated through a CI/CD platform. In our case, we use Circle CI, but tools like Jenkins are really effective ways to do this too. So that's everything we had for today. I really hope this was a helpful kind of get started quickly guide to the world of ModelOps. When people talk about ModelOps, what do they mean? Who are the players involved? We just glanced the surface on all of this. There's a giant iceberg underneath what I covered today, touching on each of these areas, each of these tools, each of the steps in the process. So join us in general if you'd love to talk more, or if you have corrections and issues with any of the thoughts that I shared. I would love to hear your thoughts, and most importantly, would love to see you back next week. So thanks again everyone for your time. Really appreciated it, and hope we can do this again soon.